How do minerals form? There are several different ways we can discuss. Minerals can precipitate from an aqueous solution because the solution has reached its saturation point. Minerals can also precipitate slowly from moving groundwater that travels through the fractures and voids in the sediment and rock below ground. In this picture here, we're looking at a very large reserve of a salt. In particular, this is lithium chloride. And this deposit formed from the evaporation of water, so it became supersaturated. The lithium and the chlorine ions became supersaturated when the water started to evaporate, and as a result, it crystallized out. In this picture, we're looking at a geode, and geodes form when groundwater travels through the rock and precipitates out various minerals. In this case, it's beautiful purple quartz we call amethyst. Minerals also crystallize from magma, molten rock. As the magma cools, crystallization of minerals begins. And the last way we can discuss how minerals form is deposition of a mineral due to biological processes. So marine organisms use calcium and silica in the seawater and precipitate out their external skeletons. And these skeletons are composed usually of calcium carbonate or silica. Corals and mollusks, such as clams, use calcium, whereas diatoms and radiolarians use silica. Here we're looking at a piece of granite, and granite is a rock that is made up of various minerals, the most common being quartz, hornblende, and feldspar. So these are minerals that have crystallized as the magma cools. Just another picture of a lava flow, and as this lava cools, minerals will crystallize. So as a rite of passage as a geologist, we must learn how to identify the most common minerals using what we call diagnostic or physical properties. These are observations and simple tests that are performed on a mineral sample, and a flow chart is then used to identify which mineral you have. Let's look at these physical properties in more detail. An optical property that is used is the luster of a mineral, and that is simply how light is reflected from the mineral surface. And we can categorize our lusters as either metallic or non-metallic. If a mineral exhibits a metallic luster, it needs to be a true metal color, gold, silver, copper, for example. If the mineral is simply shiny but not a true metal color, then we consider it non-metallic. So don't get those confused. And under non-metallic lusters, we can subcategorize as vitreous, which just means glassy, dull or earthy, pearly, silky, and greasy. This is an example of a metallic luster, definite metal color. This is the same mineral, except that it has been weathered and tarnished in the atmosphere, and so we would consider that a submetallic luster. Continuing with optical properties, the ability to transmit light. Is the mineral opaque? No light being transmitted through it. Translucent? Light can go through it, but you can't read an image or see an image on the other side. And finally, transparent, where light and an image are visible through the sample. Another optical property is color, the external color of a mineral. And this is not a great physical property to base your identification of your mineral on. That is because many minerals come in a rainbow of colors, so you need to be a little bit careful when using color as an identifying physical property for a mineral. Here's an example of the same mineral. We have purple quartz, clear quartz, yellow quartz, black quartz. So quartz comes in a rainbow of colors. So color as a physical property is not a reliable indicator of the mineral. These various colors that the quartz appears in is due to impurities in the mineral. A more reliable physical property than color is what we refer to as streak. That is when you take a mineral and powder it on a porcelain streak plate. And a mineral's external color often varies, but its streak color generally does not. So in this sense, streak is a more reliable physical property than a mineral's external color. Here's a demonstration of how streak, the physical property streak, is performed. The mineral pyrite, a metallic mineral, gold in its external color, and yet produces a black streak. Some minerals will grow and exhibit what we call crystal shape or habit. This only will occur if the atoms are not too closely packed together as the mineral grows. This is not generally what happens. Minerals generally occur as a giant mass, not exhibiting nice crystal shape or habit. But here is an example of pyrite. Both of these samples are pyrite, and they are exhibiting two different habits. Here we have a pyridahedron shape. Here is a cube. Some additional crystal habits include fibrous. This is a variety of asbestos. Blades. Agates are banded. And then cubes is a common form as well. One of the most useful physical properties for identifying minerals is the mineral's hardness. How easily does the mineral break or deform under stress? To determine this, we use the Mohs relative scale of hardness. It is a 1 to 10 scale. Students are given a test kit with a penny, a nail, glass or knife blade, and a streak plate, and your fingernail, and from that you can determine the mineral's hardness. Additional physical properties for mineral strength include cleavage and fracture. Cleavage is the mineral's tendency to break along planes of weakness. The planes of weakness are due to bonds in those directions being weaker than in other directions. So when you take a hammer and tap the sample, it will break along those weak planes and produce a smooth surface. So identifying cleavage for the beginner, the best suggestion I have is to look and see if there are smooth surfaces. So we can describe not only yes or no, the mineral has cleavage, but how many directions, 1, 2, 3, or 4, and at what degree, what angle is it? 90 degrees, not at 90 degrees. Now minerals can also fracture, and minerals that fracture along the surface, that simply is due to no weaker chemical bond in any direction than any other direction. So the strength of the bonds are equal in all directions. And so they will irregularly fracture, conchoidally fracture, splintery, and fibrous fractures. Here is the mineral mica, and it has one perfect direction of cleavage. Additional examples of cleavage: feldspars have two directions of cleavage at 90 degrees. Here's one surface. Notice the smoothness here. Here's another surface. The angle is 90 degrees. And this is not a cleavage surface, but a fracture surface. Here we have two directions of cleavage, not at 90 degrees. This is three directions of cleavage, 1, 2, and 3, and these are at 90 degrees. Halite, salt is an example. Here are three directions of cleavage, not at 90 degrees. And finally, fluorite is an example of a mineral with four directions of cleavage. So here is quartz. Quartz does not cleave. It fractures irregularly or conchoidally. Let's finish up on a couple more physical properties. The tenacity is the mineral's resistance to breaking or deforming. Does the mineral behave in a brittle fashion, like dropping a piece of chalk on the concrete? Is it malleable? Is it sectile or elastic? Density is a physical property defined as mass divided by its volume. In geology, we use the term specific gravity, and we can consider specific gravity and density as the same thing for our purposes. Most minerals have a specific gravity between 2 and 3. However, metallic minerals can have more than twice that specific gravity. Here is a list of some additional physical properties that may work for a couple of different minerals, but not a lot. Taste, halite would taste salty. The feel, if the streak smells like rotten eggs. If the mineral is magnetic, like magnetite would be. Double refraction, I'll show you an image in the next slide. And calcite effervesces when you put dilute hydrochloric acid on it. So let's take a look at double refraction and effervescence. Here's an example of double refraction in the mineral calcite. And this is a piece of calcite that is effervescing in dilute hydrochloric acid.